In this video, we're going to extend our concepts of functions of more than one variable to in fact more than two variables. And it's not hard to extend it, especially in a geometric sense. Imagine looking around the room you're in right now and thinking about the temperature at any point in space. You would imagine going to the corners, down towards the door, closer to a window. To specify the location, you would need to specify three coordinates, the x, y, and the z coordinates. So very naturally, the temperature function becomes a function of three variables. To specify the temperature, we need to know three different values before we can compute the temperature there. And we don't need to stop at three. In fact, we probably shouldn't. Imagine some other variable that we could potentially include in this function that would make the temperature a function of four variables. Well, imagine your same room that you're in right now, and imagine adding time to it. Having the temperature be a function of x, y, and z location, and then t makes total sense. Imagine, say, near a light bulb, you'd specify a coordinate of the air near the light bulb with x, y, and z, but depending on whether the light bulb is on or off, i.e. what time it is, then that would also have an effect on what the temperature is. So it's very easy, even just looking around us, to find examples where we might need more than two variables, maybe as many as four, just to even get started. There is an uncomfortable challenge with these kinds of functions, which is how do we visualize them in any way, shape, or form? In particular, if we have a graph of a function of x, y, and z, it's not even clear what that would mean, because if we think about how we drew things before, we would have had z equals a function of x and y. That was a surface. But it was a surface that lived in a three-dimensional space. We needed three dimensions to show this or display this. In this particular scenario, if we have x, y, and z as our inputs, and a fourth value as the output, we would need four dimensions to graph that in the same kind of way. So that's probably a non-starter for most of us. However, if we want to get some kind of visual sense, we can use an analog of the contour diagram. And this is the idea of picking some value of c, and that's going to represent, I like to think of it as temperatures again. Think of all the points that have the same temperature. Well, that would just be a collection of points in 3D, and that would be a level surface. Level, again, meaning the same function value, same temperature, if we're sticking with that analogy. And so that's what's level about it. But the key thing is we get a surface with that. Like with contour diagrams, if we sketch a number of these level surfaces, then we can get some kind of sense about the function and its values. A fun example that you can encounter walking around Queen's campus is a result of the steam heating that we use. If you look at one of the fields, you will see that there's usually a melted patch in it. And the reason is we have steam that's running through a pipe. Now imagine what the temperature in the earth would be around that pipe. Well, probably in pretty close to a circular or cylindrical shape around that pipe, we would have temperatures that are a little less high or a little lower than the temperature of steam, so say 90 degrees. And then outside of that, there would be another cylinder where the temperature might be 80 degrees. And if we encounter the ground somewhere on top of all that, you might see that nice cylindrical shape kind of flare out a bit, and you might see a patch, find a different color here, you might see a patch up here reaching to the ground where things are at 70 degrees. And so this idea of tubes nested in tubes captures the level surface idea. All the points that have the same temperature would have some three-dimensional location. Again, it's a little hard to sketch that in 2D, but with a bit of imagination, you can imagine those nested tubes representing levels of the temperature function and levels that have all the same temperature in each individual tube. Sometimes this can be made clear, or clearer anyway, by looking at computer-generated level surfaces. They have a little more clarity than the hand-drawn ones. There's a number of examples here, including a CT scan, where we would have density as the main feature, and this has the additional effect of adding lighting effects. And that gives the two-dimensional image a sense of proportion and depth from the lighting effect. And what we would see here is a surface defined by getting above a certain density. In other words, moving from the density of skin into the density of bone, this surface would be a level surface of that density function. If we look at MRIs or fMRIs, you're looking at different colorings based on the activity in a three-dimensional shape. We can get down to fluid turbulence. These are pods of higher turbulence. If you're looking at groundwater contamination, this is most similar to the steam example. You can imagine contaminant levels and say this blue line here, this blue surface here, defining a level of contamination that stretches into the ground that's lower than the contamination level represented by the other colors like red or yellow. But we can see that that surface is a three-dimensional surface representing a constant level of the function here, contamination. There's other examples here from electron density maps. This would be something that people use to study protein structures, or weather maps, turbulence, flow, density, or temperature of the air. Again, all of these are functions of some property, be it density, turbulence, contamination level, that are then conditional on three variables, conditioned on x, y, and z. And here's a way to at least draw those functions. For reference, we will not ask you to sketch these kind of graphs, but it's important to recognize that we can generate them if we need to.